Ramanujan for G is now available on the Google Play Store. Try it out for free.
So we continue with our discussion of um, electrostatics, but today we're going to very quickly transition to um, current electricity. Okay, remember that this is more of a learn a little but do more problem session, right? So what should you be doing? You should be getting hold of HC Verma. See, I am now showing HC Verma part 1. You should be getting hold of HC Verma part 2. Okay, and how do you go about it? You download our app from com.gyanamarga.sushruta, com.gyanamarga.ramanujan, or our newly minted CBSE 12 app, right? CBSE 12 app has only 12th standard, no 11th standard. Okay? But electricity is essentially only there in 12th standard. So you download the app, you learn from the textbook, learn from the IIT PAL lectures, learn from HC Verma, do the solved problems in HC Verma, then attempt the assessment in the app, right? Now, we have some questions, but on top of that, we also have assessment for from the other, third party, right? So you should attempt both. You should use the third party assessments as well because they have a much bigger database of questions. Okay, so that's how you proceed. And you proceed in a very methodical way. I know, IIT exam is coming, NEET exam is coming. I don't know the exact date. The original date is scheduled for May. It may get moved because it right now clashes with the CBSE exam. So CBSE is going to start from 26th, right? So it will get moved probably into June, I think. I'm not sure. You have to wait till hear from the government. Okay. Now, having said that, let us look at these questions, right? Figure shows a line of constant potential in a region which the electric field. Incidentally, I took this exam, okay, right? So, no. Now, the key thing is, the values of the potential written 40, 50, 30, 20, 10, right? So the magnitude of the electric field is the greatest at A, B, or C, right? So now the electric field is greatest. See, between here and here, the dV by dx is E, right? So between here and here, the for equipotential lines are far apart. When the equipotential lines become closest, which is between C and B, right? Between these 2 points, right? A is in between 50 and 40, and there's a lot of distance there, right? So, but between C and between these 2 lines is B, right? That's when it's changing the fastest. The equipotential lines are very, very close by. So as a result, you have a rapid change. Okay, so that rapid change leads to the greatest dV by dx. Okay, now 2 small balls have equal positive charges Q, and they are suspended by 2 insulating strings of equal length from a hook. The whole setup is taken in a satellite into space where there's no gravity. The angle between the strings is dash, and the tension in each string is dash newtons. Okay, 1 by 4 pi epsilon naught, right? So there are 2 balls, same charge, suspended by insulating strings, equal length of a hook, right? So let's go ahead. In state of no gravity, right? The angle between the strings is what? What is the angle, right? So now this angle, right, is, so what are all the forces acting on this, right? There is only one force, right? It is the repulsion, because there's no gravity. If there's gravity, you can include gravity, right? State of weightlessness. They want to know if you understand what happens. They'll go to the furthest from each other, right? Because there's no other force. it will be held up only by, so it will start like this and then go like that. So the angle between the strings is going to be 180 degrees, and the force is 1 by 4 pi epsilon q1 q2 by r square. So it is q squared by 4l square. Very simple actually, right? This is the simplest of the questions. Now these were all at a time when JE was not that difficult. Okay, now the questions get a lot more difficult. Two parallel plate capacitors of C and 2C are connected in parallel. So there is a C. So that is this. That is this kind of a question. Okay. C and 2C. This kind of a question, right? Capacitors in parallel. C and 2C. Okay. Saying there are two capacitors in parallel, C and 2C, and charge to potential difference of V. The battery is then disconnected, and the region between the plates of the capacitor C is filled with a dielectric material K. Potential difference across the capacitors now becomes not easy. Okay, so here is the thing: the capacitance is sum, right? So 3 CV, right? Q is equal to CV, right? So initially the charge is 3 times CV, right? Now that much is charged between the two capacitors. Now when the battery is removed, what happens? The charge redistributes. Okay, so what happens when there is two capacitors? There will be plus charge and minus charge. Then they disconnect the battery, and then these two are just reconnected, right? So now the potential across the capacitors now becomes what, right? So that is uh, you know the second voltage, right? What it will do is it will readjust so that the so one of them has its what is that, epsilon naught a by d, right? So K time will become, is filled with a dielectric material of K, right? So its capacity is going to become Kc, right? So as a result, the net voltage will be the same. Okay, the charge will redistribute in such a way, right? Q equals, Q is this, right? Q is K plus is 3CV, right? 3CV will equal K plus 2 times C V2, because the new voltage is what? V2, right? So now as the new capacitance is K plus 2 times C. Okay, so new voltage between the capacitance we don't know, that's what we are trying to find, right? But the new capacitance is this, right? So now the total charge is going to redistribute in such a way that it's going to produce this new potential difference across the capacitors. Okay, so so the voltage is the current is going to the charge is going to be the same, but the new voltage will be such that it's common and it is a variable such that it is equal, right? So the old charge is going to equal the new charge, right? The charge redistributes. That's the important idea. The old charge was 3C times V, right? The new charge is going to be V2 such that it's the new capacitance is K plus 2 times, right? So V2 will equal 3CV by K plus 2C. So C's will cancel, 3V by K plus 2. Okay, so that's how you solve this problem. There's also a fourth problem, but let's move on here. Let's move on here. So now the other idea deals with, this idea of dielectrics, and dielectrics when introduced into a medium, right? See, normally when you talk of parallel-plated capacitor, the medium is, we don't talk about the medium, and we talk about epsilon A by D, right? Now, if let's say the medium is air, air is a dielectric. Okay, or we talk about some kind of electrolyte, right? So what happens there is they will separate out. When you apply a voltage across the capacitor, let's say it's to make things simple, it's a direct current, it's a constant voltage, right? The dielectric will polarize. So the plus charges will go one way, the minus charges go another way, etc. Right? Now, if you have provide alternating current, then it will keep changing, and therefore there is a induced kind of, not, I won't say induced, it's a kind of current also there. Okay, another kind of current where the charges will keep changing in positive and negative. Okay, and it will go from positive to negative. The positive initial becomes positive on the top, negative on the bottom, then it will switch positive, negative when you apply a alternating current. Okay, so that's what happens with the dielectric, right? So the dielectric, it switches around the charges. The atoms don't move around. Remember this. When you pass current through a wire, copper wire, right? Only the electrons move. The atoms don't move. Okay, and there is a flow of electrons through it. It follows this drift current, right? Now, this current is not a drift current. We already discussed drift current, velocity of the electrons, JeV, etc. Right? So now this current is called displacement current. It's a different kind of current. It results from the polarization of the dielectric. Okay? Now, if you had an electric field in the dielectric, there is a polarization epsilon naught psi e. Okay, that is the polarization. And therefore, typically when we talk about we introduce this term called D instead of E, right? Electric field, we introduce this term D, which includes the second term P. P is polarization, and we say epsilon naught E plus P, and this itself is a constant of that. Okay, so now so there is a bound charge density sigma, which is the dot product of P and N. Okay, and so there is a bound surface charge density involved inside the dielectric. So now, when you have a capacitance with a dielectric, it introduces this psi, and very often we introduce a K. Okay, the dielectric constant is a K, and it is just a multiple of epsilon naught. Instead of epsilon naught A by D, we will then introduce a epsilon naught K times A by D. Okay, so that K is called the dielectric constant, and it is typically 1 plus psi. Okay, 1 plus where psi is this variable we introduce. Electric susceptibility. Okay, so these are all like details you really don't need to know, but it's worth knowing also, how these things little bit happen. You want to understand exactly how polarization happens. What is this displacement current? You should read H.C. Verma. He discusses this. Okay, different materials have different kinds of polarization. They introduce different types of dielectrics into capacitors, polystyrene, water, strontium titanate. I never knew that one. It's probably got the highest 310, right? And of course, glass. Glass breaks, right? Porcelain is often used also, but again, you got to be very careful. Titania, ceramic, I think that's a good one, right? So you want something that's, when you make a capacitor, you don't want it to break down. You don't want your cell phone to break down. You don't want your circuits to break down, right? All these things, laptop to break down, right? If you open the laptop, there'll be a lot of electronics inside there. There are chips, and there is also all these capacitors and inductors and everything. Okay. Epsilon naught A by D, K times epsilon naught, epsilon A by D. Once you introduce the dielectric, it becomes, instead of epsilon naught, it becomes epsilon, and epsilon is K times epsilon naught. Very straightforward. Just understand this, and then when you have capacitance with dielectrics, we introduce this second term called D, right? Which is epsilon naught E plus P. Okay. Now, so then you have problems which deal with these dielectrics. Parallel plate capacitor with air between the plates has a capacitance of 9 farads, 9 picofarads, right? Epsilon naught A by D gives you the capacitance measured farads, right? The separation between its plates is D. Space between the plates now filled with a dielectric K, right? So K times epsilon naught, right? One of the dielectrics has constant K1 and thickness D by 3, while the other has a dielectric 6 and 2D by 3. So fills it with two different dielectrics, right? So now these two are in series, right? It's a parallel plate capacitor, but it now introduces two capacitors inside, right? Which are in series. Initially, it is epsilon A by D, right? The new, because it's in series, the new C is C1 C2 by C1 plus C2, and C1 is the first one, which is K1 equals 3 and thickness equals D by 3, right? So now the A is the same. The D for one is D by 3, for the other is 2D by 3, right? So now your new C equals, so the C1 is what? Epsilon A by D, that is C times K1 by 1 by 3, right? K1 is what? 3, right? So 3 divided by 1 by 3, therefore it becomes 9 times, right? And so K2 is what? K2 is 6, 6 times 2 by 3. So 6 times 3 is 18, by 2 is again 9, right? So 9 and 9, right? So first one is the 3 times 3, second one is 6 times 3 by 2, right? So both become 9, right? So C1 and C2 are equal. It is, but each is 9 times, right? So 9 times 9, right? By, so if you have, instead of 1C, you now have 9C and 9C in parallel, in series. You have 9C and 9C in series. What will it be? Originally it was just 9, right? So now it is 9 and 9 in 9 times 9 and 9 times 9 in series. 9 times 9 is 81. 81 times 81 in series becomes 81 by 2. Okay, so 81 by 2 is 40.5. Okay, you can do the arithmetic yourself. Okay, so 81 by 2 is 40.5. So now you have 2 in series. That's the important thing. Then you have to know what epsilon naught A by D, what happens to epsilon A by D when you introduce a dielectric. Okay, now, so to wind this chapter down, basically we introduced this term D, which is the displacement, total current, right? D, and there is a displacement field, right? Which includes both the electric field and the polarization. Maxwell introduced D as well, or Ampere introduced D, corrected it to introduce D, I think. I'm not sure, but there is a D. So you, instead of del dot E equals Q by epsilon, right? It changes to del dot D equals Q by epsilon. So, so you have drift current, you have conduction current, right? And now you have displacement current. Displacement current is introduced by the polarization of material. So now what happens to Gauss's law with displacement current? That's what I was talking to you about. We introduced this term D, displacement vector D epsilon naught E plus P. Okay, so that introduces how when you introduce a dielectric into the equation, there's polarization. Closed interval D dot dA equals, and D is because you have that already, that epsilon, right? You just say D dot E equals Q. There's no by epsilon there, as so close surface integral of D dot dA equals Q. That's very simple, beautiful Gauss law in for electrostatics. All right. So now I'm going to quickly switch over to electricity. Okay. I don't know how much of it I will get done, okay, but I'll try my level best to kind of get you guys, really charged up with electricity. Okay, so as all of you know, and I assume we already went through all this in the previous semester with a lot of the theory. The first part of when I first teach it, I do a lot of justice in the theory. The second time when I teach it, I kind of get to the theory, but then I spend a lot of time in explaining the actual ideas, right? The actual problem solving, right? So current is what? dq by dt, the rate of flow of charge, right? So that's the first idea you must know, and you can never forget that. Current is measured in amperes. It is ampere is just coulomb per second, right? dq by dt is what? Coulomb per second. Rate of flow of charge, coulomb per second, right? So now basically just like water flows, just like this flows, that flows, right? Air flows, right? Current flows. Current flows you from the negative charge of from the anode, right, to the cathode, right? But actually the electrons flow the other way. So that's the first thing you must remember. Current flows from positive side to the negative side. Electrons flow the other way. Insulators, metals, and semiconductors. This. You may not have yet heard of. You should have, if you had listened to the lectures. I spent a lot of time discussing semiconductors. Most recently, I discussed semiconductors as I brought the semester to a halt. Right now, in the case of the, like for instance, this basically you think of a battery as a charge pump, which then keeps pumping charges into a circuit, right? Keeps pushing charges in, stuff happens, and then it returns. It's electricity is a form of energy that is transferred from your power station somewhere and sold by your utility, right? We in Tamil Nadu, we used to have Tamil Nadu Electricity Board. Okay? They would provide a bill every month. Delhi Electricity Board provide a bill. Bijli bill, right? Bijli bill aa gaya, right? And some places they try to, typically Bijli bill is indexed, right? Anyway, let me not get caught in that, right? Bijli bill is indexed. That is, for the first so much, they charge less, then they charge more. For industries, they charge more. Okay, very typical. Farmers, they charge less. Homes, they charge less for a certain amount, then they charge more. But if you put your AC on long time, it will show up on your. Now, if you if you run an industry, unless it is a subsidized industry, you will get a full bill, okay? Because they have to charge someone. Okay, so that's why it is like that. Okay, finally, they have to run a business. An electricity board buys electricity from someone and sells the electricity to someone else. Okay, so they have to run a business. Now, dq by dt is the rate of flow of charge, right? Current is the rate of flow of charge. There is a current density, J dot dA equals I, right? So J is a vector. Okay, so the rate of current density is a vector, the rate of flow of charge, right? So now, so typically you have the velocities of different electrons are uncorrelated, right? So that is the electrostatic. If there is no condition, then all these electrons, they kind of move around, but then there is a net flow in a certain direction. Now, the electrons are accelerated; they kind of like just flow fast to, and J equals E and V, right? So we discussed all the J equals E and V last time, right? So I'm not going to go into that. I'm going to, of course, talk to you about resistivity, right? Rho L by A, rho is the resistivity, where it is 1 by sigma, where sigma is the conductivity of the particular material. Ohm's law states that J equals sigma E, where sigma is the conductivity, and this leads to the more important formula, V equals IR, V equals IR. Now, rho equals E equals J So E equals J equals sigma E, E equals rho J, right? J equals sigma. Sigma and rho are, one is the conductivity, sigma is the conductivity, rho is the resistivity. One is the inverse of the other. Okay. So now you can also have, just like you have resistance, you can also have conductance. Conductance is measured in Siemens. Okay. Conductance is measured in Siemens. Resistance is measured in ohms. All right. So voltage by amperes, voltage measured with volts, volts by amperes equals resistance. Ohms equals ohms. Resistance. Okay. Ohm. Rho L by A gives you the resistance. All right. So thicker the wire, less the resistance. Longer the wire, more the resistance. Okay. Rho L by A. Okay. So then you have charge flow is similar to heat flow. There is also Ka dt by dx, right? If you look at the temperature conductivity, right? There is a temperature gradient like that, dq by dt, sigma A dv by dx. Okay. There is a, just like heat flow, you can think of it as a charge flow. Okay. So one must be little careful in understanding these ideas, but I don't have a lot of time to again re-explain this. So understand these ideas, read about the drift velocity, etc., and like all these details about the collisions, right? Drift velocity and how there is a mean free path and all that. So you should only read about it in your by reading H.C. Verma one more time. Okay. So now V equals IR, J equals sigma E. Okay, and then you have this idea that resistance is a the rho, right? The resistivity varies with temperature. Okay, so what does that mean? Resistivity varies with temperature. Okay, so in any laptop, right, you will notice that there's a fan. Okay, the fan is aimed at cooling the laptop. Why do they cool the laptop? It is to keep the circuits inside the laptop operating within certain temperatures. In many countries, notably in the extremely hot countries like India, in the summer, it is they typically put on the AC essentially for the laptop. There are 50 people in office, we have very good AC because they want to protect the laptops. And of course, the people also, you do more work when you are working within in temperatures within certain degrees, right? So then you have this carbon resistance and you have those bands of the resistors. So you should also remember to how to understand those bands, right? So resistance at zero, so you have 1 plus alpha times delta T. So resistance at zero, resistance at 25. So 1 plus alpha times resistance delta T. Alpha is the coefficient of linear expansion, right? Beta is the coefficient of temperature coefficient, linear expansion. This is resistance expansion, increase, right? Coefficient of resistance with temperature. Okay? So 1 plus alpha times delta T. So as the temperature goes up, the 20 degrees, so you'll have R naught plus 1 plus alpha T. So you think it's they say it's a linear increase. Okay, it means typically a lot of things, the second degree term they will drop it for small changes in temperature, higher changes they will introduce that. So now then we introduce the electromotive force, then we introduce rho L by A, right? And then we looked at the internal resistance of a battery. Every battery has itself resistance. It of course is a charge pump, produces has a fixed voltage, typically 1.5 volts. So if you put two batteries in series, it will be 3 volts, unless you connect them upside down, in which case you get no volts, right? So if you connect them correctly, you'll have 1.5 plus 1.5 plus 1.5 series. You can also connect them in parallel, right? So what is the aim of all this, right? The aim of connecting them, see, you increase the voltage. If you want to keep the voltage tight, and you have this, parallel, right? So now, see, you can build these combinations of these batteries and use that, like, Now with all these EVs, right? There are many ways to slice and dice that. That's a very complicated business, and I'm not going to go into the details of that. You must understand, voltaics, electrochemistry. They will teach you voltaics. You go talk to Professor Tiwari, he will teach you a lot about this. He's a real expert in this. You go talk to him, spend half hour with him. Okay, say sir, I want to learn. And he will be very happy to teach you. So now, see, you have a resistor, then you have a voltage, right? And so now V equals IR. See, finally, most important idea is V equals IR, where R is the R total. When you have when you model a battery, you model it as a voltage with a positive line. Bigger line is the plus, right? Small line is the minus, right? Remember that bigger line is the plus. Always never forget that. Then it has internally within it a internal resistance, right? so, so what is the open circuit voltage? Open circuit voltage is what? 10 volts. Why do they call it open circuit voltage? Because there's no current. At the time when you talk about the open circuit voltage, there's no current. But when you start supplying current, the battery itself will have a resistance, and some of the I will go through that R, through the internal resistance as well. So if you add a load resistance, see, you always in electronics or in power electrical science, you always look at everything as a box, because systems thinking. Okay, I supply power from somewhere, I have a box. My laptop's a box, right? So, and it's a system, it's a black box. Inside the black box, what all you do, how you manage the black box, etc., is what you're really concerned. You say from the outside I'm getting power, inside I drive a box, I manage and control it. Very important idea. Control of the circuits in a box. So if the load is RL 4 volts, right? And so then you have little r plus RL. So little r plus RL gives you the total resistance. So V equals I times RL plus R. Okay, and then therefore I equals uh, 10 by RL plus R. 5 equals 2 amps. All right. So now you then end up with these simple circuits, and you can use that to define the V equals IR, right? So then we introduce this this idea of power, V square by R, V times I, they're all power. Okay, V times I will give you the power that is being drawn. Power is what? Work per second. Okay, so remember that. So and then use this J equals sigma E, etc. if it came to that. Okay, so but the most important salient parts of this deal with solving circuit problems with the current and voltage and everything else, right? Finding the current and solving multiple equations. Multiple nodes, these are all linear equations. So you'll have simultaneous equations, and you'll have as many simultaneous equations and needed to solve the problem, right? So you count the number of loops and you create the number of equations, but there is some cleverness that you can use. Okay, so that is a very important part of this whole idea. Okay, so so the power delivered by a circuit is dW by dt, where W is the work. Okay, so the circuit draws power. I have a a lamp up there, right? A bulb up there, right? So the power drawn by different circuits to produce light. What is the aim of having a bulb? Light, right? That is dependent, right? Partly also on the heat that it emits, right? Like the traditional bulb, right? Why does it suck so much power compared to these LEDs, right? It is because a lot of the power goes in a resistor, goes as off as heat loss. Okay, so like even in the laptop, right? The power of the laptop is an extremely important idea. cell phone, right? This cell phone, right? There are many parts to it. One is the display. The other is the electronics inside, right? The display is also in some ways it's an LCD or an LED. OLED is now a popular type of display. Okay? These displays also like it's like a light source, basically, So you can think of it like also a little bit like a bulb. So it also has a constant draw of power, as does the electronics inside the cell phone. Okay, and so there is a constant heat loss from the resistors in the circuits inside. Okay, now there are other elements like the capacitor, which we looked at before, and the inductor. Every capacitor will have some internal resistance. Every inductor will have some internal resistance. Now, the total net sum total of all the resistors is going to produce your um, um, is going to produce the lead to the net power dissipation. Okay. Now, a friend of mine once told me, okay, that every chip, you can think of it as a big capacitor. And I was amazed at how he looked at the world. And he's a fantastic electronics engineer. Okay, so but then let me get on with my business here. Power is I square R or V square by R, and V times I will give you the power. Okay, so and then therefore with an increase in temperature, there's more power dissipated as well. That's why they also use a fan to cool the laptop. The fan takes energy, right? So that's a different type of mechanical energy. When you use the fan, you have two. One is you have resistance, then you have the energy to make it spin. That's a different type. Okay, that's when you look at when you look at electromagnetic induction, which is the other way, and then you look at the power circuit, right? You drive basically you drive a magnet, right? And you convert the electrical power to mechanical power, back to mechanical power, right? So so then P equals I square R or V square by. So now when you have a long power line, you also have power loss in that line. Okay? But and therefore you can calculate. But then the most important thing is V equals IR, and you must know how these things operate when there are cell combinations and when there are complicated circuits involving voltage and resistance. So cells in parallel, what happens? Cells in so in parallel you have they will readjust based on the internal resistance, right? So here there are two cells in connected in parallel. What is the net? And you want to take this and you replace it with that, make it one cell and one resistance, right? So how do you do that? So you say VB1 minus, so you have the net current coming in is equal to the net current going through this, right? And the voltages are known. E1, the open circuit voltages are known, right? So now what they are telling you is that the net voltage is this, equivalent voltage is this. And how do they do that? They are saying VB1 minus VB2, right? So if this B1 is the voltage here, B2 is the voltage here, the voltage difference between B1 and B2 is V, and that is E1 minus IR1 or E2 minus IR2. So that relates these two, right? But then you also know that the net I equals I plus I2, I1 plus I2 from Kirchhoff's junction rule, right? So now the net I equals I1 plus I2, it's equal to E1 minus V by R1. Okay, so that is from Kirchhoff's voltage law. So V is the voltage across this minus E1 divided by R1 will give you I1 plus E2 minus V divided by R2 will give you the current in this branch. So you add the two currents, you'll end up with I1 plus I2 equals I. Therefore, you refactor it, you'll end up with this I times R1 R2 by R1 plus R2 plus this second term. Okay, so then you can rewrite the equivalent resistance and you can rewrite the equivalent voltage. Okay, so so having figured that out, you can then, so this is the equivalent resistance, this is the equivalent, this is the equivalent voltage, and this is the equivalent resistance to cells in parallel. So that's how you derive that. Okay, so now if you have to rederive it in a different circuit, it does the same thing. Remember to use basically the same laws that you do use. One is the junction rule, the other is the loop rule, and then you know how to do this. But learn this, and you will be able to solve any of these cells in parallel, cells in sequence kind of problem. This is, so there is an actual current which is the equivalent. You're taking something and you replace it with another circuit. So that's what he is teaching you here. Okay. Now, Kirchhoff's laws, there are two laws. In any closed loop, you go once around the loop, you will end up with zero, right? Any closed path of the circuit, the starting point, you go one full circle, you end up with zero, right? And at any junction, the current coming in will equal the current coming out, because there's no charge stored at any place in a circuit, right? Charge just keeps circulating, right? So that is the basic idea in Kirchhoff's, sigma II equals zero, junction law, and sigma VI equals zero, loop rule, and then you use these two rules to then, but then what you want, most important thing is the big line and the small line, they dictate the big line, current goes from the big line to the small line. The electrons go the other way. Small line is the cathode. The electrons go this way, current flows the other way. That is always the convention. Then you draw your directions, you write down the unknowns in terms of the currents, and then you solve for using the voltage and current rules. You'll have as many equations and unknowns. Okay, so if you use only loops, if you have three loops, you use three loops. You'll have three equations, three unknowns. Three currents, three equations, three unknowns. Okay, that's how you have to go about this. Don't get very confused in terms of the unknowns. Graph theory tells us that you can solve pretty much every resistance circuit, but in some cases you have to a little bit understand also the Wheatstone bridge, because that will simplify the way you can solve these problems. But you can always solve any problem with just three equations and three unknowns, or four equations and four unknowns, based on the number of loops, using the number of graphs in terms of the equations. So if you had a circuit like this, typically you have one loop here, second loop here, third loop here, and then you have a net. You'll have a net three equations, and you should introduce only three unknowns, and you should frame the equations in such a way as to calculate them. But now here, all he is doing is, he is saying, let's say you start at this point, right? Plus 8 plus V1 minus V1, because this is plus and this is minus, right? So plus 8 minus V1 plus minus 8 minus V1 minus 8. So when you go for plus to minus, he's saying that's the negative. Convention is negative. So minus 8, then minus 8 again, then plus 6, plus 10. You come back to 8. So he's going one full circuit around this. That will also give you 0. Otherwise, you can just go three loops, this loop, and this loop. Three loops and three voltage equations, and internally you reduce the unknowns using the junction rule. You need only three unknowns here in terms of the currents. Okay, so that's the critical thing. So here you have only one loop, so introduce only one current, right? And therefore that current is I, and all the elements in series will, the same I will flow. Okay, so keep that in mind, and then you solve these current problems. Okay. So I think we are nearing that point when the hour is ending. So so there are all these questions. So now then we introduce this idea. Sometimes what you can do is, if you have two resistors in parallel, like in this case, you replace it with an equivalent. 6 and 6 in parallel is a 3. Okay. If you have two resistors in series, you just add up. R equals R1 plus R2. There are two resistors in parallel. It is 1 by R1 plus 1 by R2 equals 1 by R. Right? So it is the inverse of the capacitance. Capacitance in series, 1 by C equals 1 by C1 plus 1 by C2. Right? Capacitance in parallel, C1 plus C2. Right? Resistance is the inverse. Resistance in series, R1 plus R2. Resistance in parallel, 1 by R1 plus 1 by R2 equals 1 by R. Okay? And then learn this Kirchhoff's voltage rule, and remember the important point with respect to how many equations and how many unknowns. Do a lot of these Kirchhoff's problems because these are very easy questions. Okay, once you learn and you understand this, you don't learn to not make silly mistakes with this, you will get all the marks with this. You will just be able to easily do the arithmetic and easily solve these problems. NEET, actually, you will not get that many of these questions, but you must know how to solve some of these problems. NEET also does ask a few numerical questions. You must be ready to solve them, but then you must understand, power. You must understand voltage. You must understand, importantly, Wheatstone bridge, and also these clever infinite equivalent circuit problems. Okay, everything, there's also a certain numerical aspect to this, right? So what I suggest is use all these to try to solve these problems correctly. Okay, so infinite equivalent circuit, etc. All right, and so um, um, I could not get through to the point where I wanted to do problems. So I will start with this symmetry-based problems before I go to our own problems. Symmetry-based problems. Then I'll do what is that? Wheatstone bridge, meter bridge, and then I'll go to the solving these problems in the next class. But I'm going to do at least one problem. Okay. So in the circuit shown in the figure, the heat produced in the 5 ohm resistor due to the current flowing through it is 10 calories. What is the question? Heat here is 10 calories. So what can you say? V square by R here is 10 calories, right? So V square by R, why did I write it as V square by R? Because V is the same, these two resistors, you just add it up, it's 4 plus 6, 10, right? So now the heat generated in the 4 ohm resistor is what? Right? So to understand the heat generated in the 4 ohm resistor, right, you have to find out first the current through it. Okay, so for that you first find out the voltage between these 2 points. What is the voltage between these 2 points? Voltage between these 2 points, the power is what? Power is 10, right? 10 equals V square by R, right? So V equals square root of 10 times 5. 10 is the power, resistance is 5, therefore 10 times 5, square root of that is, so 5 root 2, right? 5 root 2 is the voltage. Now, if you apply a voltage across this of 5 root 2, what is the current? 5 root 2 by 10, right? So 5 root 2 by 10 is the current. I square times 4, I square R, right? So I square times 4, right? I was calculating the total power. You don't need the total power, right? So I square times 4. I is what? 5 root 2 divided by 10. Okay, so let's write that, right? I4 equals 5 star square root of 2, right, voltage by 10. right? Therefore, P4 equals 25. So that is what? That is equal to 1 by square root of 2, right? So P4 is what? I square star R, right? Right? So that is equal to what? I square is what? 1 by 2. Star 4 equals 2 calories, right? Very simple. Once you know these problems, that's why I'm telling you to pay careful attention in solving these problems, because it's not difficult, right? The current I in the circuit in the figure is very straightforward. Okay, so this one is actually the easiest problem you can get. That's why it's only 1 mark. Okay, now these two are what? In series. So 30 plus 30 is 60. So you have a 30 plus a 60 in parallel. 30 plus 60 in parallel is what? What is the effective resistance? 60 times 30 divided by 60 plus 30. 60 times 30 divided by 60 plus 30 is what? Is 60 by 3, 20. Okay, so you have 2 volts and you have 20 ohms as the equivalent resistance, right? So V equals IR, right? 2 divided by 20, 1 by 10. Okay, very simple question. Very simple question. Okay, so I'm going to leave you to look at this question, but I'm going to do this next class because this is not as straightforward as those, and I want to cover Wheatstone bridge before I look at this problem and this problem. Okay, so I will do those 2 problems next time, but my aim in doing these 2 simple problems was so that you get the hang of it. It's not that difficult. Current electricity is a little bit easier, but we also did a little bit of the capacitor and material around that. But see, you really focus on 4 areas in electricity and magnetism. Okay, capacitance, electrostatics, current electricity with the direct current electricity with alternating current, electromagnetic induction, transformers, etc. Okay, and if you understand these 4 ideas, a little bit of Ampere's law, etc., that's a lot of material actually, but get your hands around that material, right, and build confidence around that material. This is the last one of the last pieces of the puzzle, right? Then you go to your modern physics, semiconductors, and truth table and all that. Okay, so that is another section. So these 2 sections are a very important part of class 12 understanding. Okay, and so I first teach this in a detailed sequence, so that you build. First time I teach it only with theory. Second time I teach it with theory and with problems. But then it's for you to take the next step in terms of getting your hands completely around all the problem solving. Okay? So I do want you to pay careful attention to that. I want you to really make a effort here. All right. So with that, I'm going to stop and I'm going to let this come to a conclusion, and then we'll look at this again next class. Okay. So I'm going to see you again next class. But then before that, I want you to do exactly the things that I tell you. App, HC Verma, your own assessment, the look IT PAL lectures, right, and extra assessment. All right, I'll see you again next week. So with that, I'm going to end, and stay safe, folks. Wear your masks every day to school.